Picture Earth merged into one huge landmass. A harsh sun sets on deserts the size of countries. Mega monsoons flood the coasts. When inland rivers go away, they come back as flash storms that move whole woods. Sharks hunt on reefs that are shallow and as rare as gold. Where corals haven't formed yet, sponge reefs grow. On land, saber-toothed gorgonopsians are the hunters, and tusked dicynodonts feed in groups. Oxygen is escaping, heat is rising, and the planet's plumbing is beginning to break down. This is the world in the Permian, which is unstable, harsh, and set on a thin edge. We'll walk Pangea from the dune sea to the reef wall in an hour. Along the way, we'll look for the masters of the sky and the land and read the rocks for the first signs that things are about to change. Pangea supercontinent. Consider yourself in the middle of a world that is now fully put together. During the late Paleozoic, large tectonic plates crashed into each other. Around 299 million years ago, in the early Permian, all of Earth's major landmasses joined together to form a huge supercontinent called Pangea. It went almost from north to south and was shaped like a huge sea. It held Panthalassa, the largest ocean, and the smaller Paleotethys Sea close to its edge. The world looked pretty easy from above, one landmass and one ocean. But that ease of use hid a violently complex side. Pangea's creation was the end of a long geological marathon. Continents that once drifted separately, Laurasia in the north, Gondwana in the south, smashed together through mountain-building collisions known as orogenies. The Appalachian-Variscan belt snaked through what's now North America and Europe, while the Urals rose where Siberia met Kazakhstan. Every impact squeezed ocean basins shut and thrust new peaks skyward. Massive forces folded rocks like paper, locking ancient seafloors deep within mountain roots. These scars still run through today's landscapes, from the Appalachians to the Urals, silent witnesses of that once unified world. The unification of continents changed more than geography. It rewired the planet's climate system. With so much land clustered together, moisture had trouble reaching the interior. Warm, wet air dropped its rain along the coasts and spent itself before crossing thousands of kilometers of desert plateau. The heart of Pangea became bone dry, a realm of shifting dunes, salt flats, and seasonal rivers that vanished into dust. Yet along the margins, monsoonal storms thundered, powered by huge temperature contrasts between land and sea. The result was a planet of extremes: drought in the center, deluge at the edges. Such vast interiors also affected temperature regulation. Oceans act as thermal buffers, moderating heat and cold. But on Pangea, distant seas couldn't keep pace. Summers in the interior scorched, winters froze, and temperature swings could break rock and bone alike. These oscillations shaped the evolution of animals and plants that learned to endure cycles of scarcity. The thick skins, burrowing habits, and drought-resistant seeds that mark late Permian life were born of this unstable stage. River systems across Pangea told the same story. Because rainfall was seasonal, streams often braided and broke apart, leaving red-stained floodplains baked under the sun. Evaporate basins formed where lakes dried repeatedly, depositing layers of salt and gypsum. These bright minerals would later help geologists trace the outlines of vanished inland seas. Every drought, every flood, etched another chapter into the supercontinent's diary. Moving plates of rock never really stopped, even when Pangea was at its highest point. Faults groaned as the crust was pulled down on them, and early rifts showed where future breakup lines might be. Close to subduction zones on the Panthalassan rim, volcanic arcs burned, sending marine crust back into the basement. Deep inside, convection currents were moving around like motors that were waiting to break the supercontinent apart millions of years from now. Earth had temporarily come together, though. This unity also shaped evolution in subtler ways. With continents fused, animals and plants could migrate almost anywhere over land. No ocean barriers stood between the ancestors of mammals in the south and amphibians in the north. Species mixed, competed and adapted to the new variety of climates. This great biological exchange helped spread dominant groups like therapsids across multiple regions. Fossils of the same creature now appear in what are today South Africa, India, and Russia, proving the connectedness of that lost world. Yet Pangea's size also carried a cost. When environments turned hostile, there were fewer refugees. Inland deserts expanded, shallow coastal habitats shrank. Many marine organisms depended on those shelves for survival. But Pangea's long, unbroken coastline left little room for broad continental seas. Life crowded into narrow ecological zones, making ecosystems more fragile than they appeared. The stage was set for instability long before the final catastrophe arrived. Panthalassa dominates. During the Permian, the Panthalassa Ocean covered almost 70% of Earth's area and went out to every horizon. It was a real ocean of the world, huge, deep, and almost never-ending. If you were on the coast of Pangea, the sky would have been eaten up by the planet's curve long before any land showed up again. It could have been thousands of kilometers to the next continent. The sea was huge and alone, and its size ruled almost everything about the temperature and life on Earth. Currents within Panthalassa were enormous engines of heat. Because there were no major land barriers, water could circle the globe almost unbroken, distributing warmth and nutrients on a planetary scale. But this same openness created strange consequences. The deeper waters were often still and poorly oxygenated, while the surface layers shimmered with motion. With fewer shallow continental shelves, marine life clung to isolated reefs and slopes that lined Pangea's coasts. Entire ecosystems existed like beads around a single bracelet of land. Scientists studying ancient rocks find chemical fingerprints of how Panthalassa breathed, or rather, how it sometimes failed to. In certain layers, the ratio of sulfur and iron reveals periods when the deep sea turned anoxic. When circulation slowed, oxygen-starved waters spread upward, suffocating bottom life. In those times, vast stretches of the ocean floor became barren muds populated only by hardy microbes. It was a quiet warning of what would one day become global collapse at the end of the Permian. In spite of this, Panthalassa was full of life in the shallows and high up. Planktonic algae made food for clouds of zooplankton and small crabs by photosynthesizing in tropical suns. The shells of the ammonoids and nautiloids were marked with complex sutures, and they moved in beautiful swirls. Sharks roamed near upwellings, and so many of their teeth fell to the bottom that whole beds of limestone are made of them. Ray-finned fish, which are relatives to most modern species, were able to adapt to every environment. On the other hand, the few remaining trilobites clung to cooler shelves near the poles, but their numbers were dropping. The reefs along Panthalassa's rim were masterpieces of slow construction. They were not built by corals, those would come later, but by sponges and calcareous algae that created thick, knobby frameworks. These reefs served as fortresses for countless species. Brachiopods filtering water, crinoids waving feathery arms, and mollusks grazing across algae-encrusted stones. Waves from the open ocean thundered across them, breaking white foam that could be seen for miles. Inside those lagoons, life flourished under relative safety, an oasis before the world began to unravel. Storms on Panthalassa were forces of unimaginable scale. With no major landmasses to interrupt wind paths, waves could grow for weeks before striking anything solid. Coastal dunes and deltas along Pangea's edge record layers of storm-deposited sands, meters thick. Some storms were likely equivalent to modern super typhoons, reshaping coastlines overnight. Their power may even have influenced the distribution of early amphibians and reptiles, forcing them inland or into new habitats. The ocean also helped maintain Pangea's extreme climate contrasts. Warm equatorial currents intensified evaporation, feeding those seasonal monsoons that hammered the continental edges. Meanwhile, cold polar waters slid northward, but with few obstructions, mixing was inefficient. This separation trapped heat at low latitudes and deepened cold near the poles. In the fossil record, that imbalance appears as alternating belts of evaporates in the tropics and glacial deposits in the south. The system was global, delicate, and prone to tipping. Geologists don't know much about Pangea from rocks because its crust has been sucked up by subduction for a long time. Instead, they know about it from pieces that have been kept on continents. Ophiolites are pieces of marine crust that have been pushed onto land. They record radiolarian cherts and basalt pillows that were miles underground in the past. Together, they draw a ghostly picture of an ocean that may have held 90% of the world's seawater but is no longer there. The Pacific Ocean is still its only living relative, and its rough waves carry the memory of those Permian currents. The ocean animals in Pangea changed over time to fit their world's openness. Hybodont sharks with flowing tail fins chased food across wide shelves, while cephalopods used jets to get away. Every living thing had to deal with huge gaps. Food chains were very thin, and when the amount of plankton dropped, whole communities could die out. Because of this, sea life was easily hurt by changes in temperature or chemistry, which was a deadly flaw when the Earth started to get too hot. Mega monsoon climate. When countries join together, the weather can't be controlled. The climate during the Permian period did more than just make rain. It also planned whole yearly shows, like the mega monsoons that hit the coasts of Pangea with great accuracy. In the summer, hot land pulled wet air into the country. The winds changed direction every winter and blew back across the Pangea. These changes in wind and water changed almost every environment at the time. Their beat could be heard in forests, fields, and rivers. Geological evidence for these colossal monsoons lies written across the sedimentary record. Layers of alternating red mudstone and sandstone show repeated flooding followed by long drought. Ripple marks point to shifting wind directions. Fossilized plant roots appear in mud-cracked surfaces, frozen mid-transition between wet and dry seasons. In places like the Karoo Basin of South Africa and the Moenkopi Formation in North America, entire rock stacks preserve this pulse. Rain, flood, desiccation, repeat. The sheer size of Pangea made differences stand out more. With such a huge landmass, the temperature difference between the water and the mainland grew very large. When the sun baked the center of the continent, hot air rose like a huge chimney and drew in water from the seas around it. Storms grew stronger as they moved toward land very fast. Some were hundreds of kilometers wide and had rivers that cut valleys in just a few days. Then, as the seasons changed, the wind shifted, pulling cold, dry air back over the ocean from the deserts inside the country. This started the cycle all over again. These mega monsoons didn't just bring water, they carried nutrients. Rivers swollen by storm runoff dumped sediments rich in minerals into coastal seas. That influx fed plankton blooms that, in turn, sustained entire marine food webs. Each storm season rejuvenated life along the margins of Pangea. But between seasons, the same rivers dwindled to trickles, leaving cracked plains and isolated ponds. Amphibians and early reptiles had to adapt to both extremes, developing strategies for drought survival such as burrowing, estivation, and tough-shelled eggs. Plant life mirrored these rhythms. In wetter zones, seed ferns and early conifers grew in dense stands along floodplains. Their roots anchored the soil, but when storms came, uprooted trunks floated downstream, forming fossilized logjams we find today. Farther inland, drought-hardy species took over, plants with thick leaves and deep roots able to withstand months without rain. The global vegetation map of the Permian was a patchwork quilt stitched together by the monsoon's reach. Over time, the monsoon belt itself shifted. As Pangea slowly drifted northward and the poles warmed, the most intense rain bands migrated as well. Regions that had once been lush transformed into deserts within a few million years. The fossil record shows this in stark contrast, coal layers giving way to red beds, fern fossils replaced by the tracks of reptiles. Climate wasn't just background noise, it was the sculptor of continents and the editor of life's story. Even the colour of rocks testifies to the monsoon's duality. Iron minerals oxidised in the dry season, tinting sediments deep red, then turned grey or green under reducing waterlogged conditions. These rhythmic changes are so regular that modern geologists can use them like tree rings to estimate seasonal cycles and even ancient day lengths. Earth's rotation was slightly faster then, about 21 hours per day, but the rhythm of wet and dry ruled more decisively than the clock. It had a huge effect on animal movement. Dicynodonts and parasaurs probably moved with the rain fronts to find brief places to graze. After them came predators, like gorgonopsians. Long, parallel fossil tracks may show these travel routes. They were carved into riverbank muds that hardened in the sun of the next dry season. Even though life is fragile, it moved in perfect time with the mega monsoon. But balance can become a trap. As atmospheric carbon rose from volcanic activity, temperatures climbed. Monsoons intensified beyond stability, sometimes turning landscapes into alternating infernos and flood zones. Vegetation that once stabilised soil now burned or eroded, feeding dust storms that dimmed skies for months. When the Earth's natural systems stretch this far, small changes can tip them into collapse. And by the late Permian, that tipping point was already drawing near. Arid, continental interior. There was one of the toughest conditions Earth had ever seen in the middle of Pangea, far from the ocean's moisture and the cool air of the sea. It was a trapped furnace in the dry heart of a continent. Millions of square kilometres of desert stretched from what is now Texas to the middle of Asia. Sand dunes rose higher than churches, and the wind blew their grains across endless fields in soft sheets. Life clung to any shade and water it could find in this dry heart of the earth, where it might not rain for decades. Geologists called the sedimentary remains of these ancient deserts ergs, preserved in bands of cross-bedded sandstone that today form monuments like the Coconino Sandstone of Arizona or the Rotliegend of Europe. Each layer records shifting dunes sculpted by winds that could blow for weeks without obstacle. The grain patterns, the angles, and even the ripple marks are identical to those found in modern deserts such as the Sahara. Through them, we see the fingerprints of a climate that swung between intense heat and sudden, violent storms. Daytime temperatures in Pangea's interior often exceeded 50 degrees Celsius. At night, without ocean humidity to trap warmth, the same sand plains could plunge toward freezing. These brutal swings fractured rocks and dried soil into a patchwork of cracks. The atmosphere itself was thinner in oxygen than during earlier ages, making breathing harder for land animals. Yet even here, life refused to surrender. Reptiles with scaly, water-retaining skin replaced amphibians that once needed moist breeding grounds. Seed plants, with their drought-resistant reproductive strategy, thrived where spore-bearing ferns could not. In between the sand seas, there were some living things in the landscape. During the few yearly rains, rivers, called wadis, cut winding paths through the dunes. Those rains came on quickly and were very bad. They were like rivers that moved sand and rock like they were walls of water. The tubs they filled would burst with life for a few weeks. There were lots of new shrubs growing, lots of bugs, and small snakes coming out of their holes to eat and breed. The water then disappeared as fast as it came. It left behind cracked mud, evaporate crusts, and frozen tracks that were baked hard by the sun. Many of the world's oldest salt and gypsum beds were born in these same environments. As inland lakes evaporated under unrelenting heat, minerals crystallized layer by layer, recording each dry season like a page in stone. The result was a shimmering landscape of white plains, chemical deserts reflecting sunlight back into the sky. These bright surfaces helped intensify the planet's heat, further drying the interior in a feedback loop that pushed conditions ever more extreme. Plant fossils from these zones tell a story of adaptation and retreat. Glossopterid forests that once fringed wetlands in the south gave way to open scrub, dominated by conifers and seed ferns with tough, needle-like leaves. Their roots anchored shallow soils, preventing total erosion, while thick bark protected them from fire. Charcoal deposits confirm that wildfires swept the interior regularly, ignited by lightning in the tinder-dry air. Afterward, ash enriched the ground, fueling brief bursts of regrowth before the next drought. The animals that survived here were specialists. Dicynodonts, beaked, tusked therapsids, likely browsed on hardy shrubs, storing moisture in their bodies much like modern desert mammals. Small, lizard-like reptiles hunted insects beneath rocks, and amphibians persisted only in the shadowed edges of shrinking pools. Fossil burrows reveal communities that took refuge underground, escaping heat and preserving humidity. These creatures lived in rhythms dictated by scarcity, active in the brief cool of dawn, retreating before noon, waiting for the rare gift of rain. The dust from inside didn't stay put. It was moved by winds over thousands of kilometers, covering coastal plains and open seas with fine red silt. Over time, these grains in the air turned into the red beds that color a lot of Permian rock today. They are the dust from deserts that are very old and have been drawn into the fossil record. Their haze must have made the sky glow, turning sunlight into orange and red tones. It must have looked like a world where it was always sunset over endless dunes. From icehouse to hothouse. The Permian period started with the last bit of cold from an ice age and finished with suffocating heat. It was one of the most dramatic changes in Earth's climate history. In the early parts of the period, southern Gondwana was still covered in ice. These glaciers cut deep valleys through what are now South Africa, India, and Australia. As they moved forward and backward, they left behind striated bedrock, dropstones, and thick layers of tillite that show how cold it stayed. Low tides made the seas look like they were frozen, and the sky over most of the southern hemisphere was pale and cold. But this fixed peace didn't last long. In the center of the world, fire was taking shape. As Pangea's tectonic plates locked into place, volcanic arcs erupted across its edges, pumping carbon dioxide into the atmosphere. Each eruption added to the slow accumulation of greenhouse gases that trap more heat from the sun. Over millions of years, the balance tipped. Ice sheets melted, runoff flooded coastal plains, and the global thermostat began to climb. Oceans warmed, deserts expanded. The transformation from an icehouse Earth to a hothouse was underway. A shift that would reshape life from the seafloor to the sky. The evidence for this warming is written into the chemistry of ancient rocks. Ratios of oxygen isotopes in marine fossils record rising seawater temperatures. Coal deposits give way to red beds and evaporites, proof that humid swamps were replaced by dry plains. Even fossil pollen changes in response. Moisture-loving plants like ferns decline, while conifers and seed ferns adapted to drought multiply. Across every continent, the story is the same: retreating cold, advancing heat. At first, the transition opened new ecological opportunities. As glaciers vanished, fertile floodplains and deltas emerged, supporting forests and rich soils. Rivers meandered across warm basins, and life seemed to flourish under the new sun. Amphibians spread into wetlands. Therapsids diversified into hunters and grazers. The warmth, for a time, was a gift, but warmth without balance becomes a weapon. As greenhouse gases continued to climb, the atmosphere thickened beyond what ecosystems could handle. By the Middle Permian, the Earth had entered a true hothouse state. Temperatures near the equator soared, and seasonal extremes reached new records. Shallow seas evaporated faster than rainfall could replenish them, leaving behind vast salt flats. On land, fires burned longer and hotter. oxygen levels dropped from their carboniferous highs, making breathing more difficult for large animals. Those adapted to cooler climates, especially amphibians and certain plant groups, began to disappear from the fossil record. The biosphere was already under stress, even as it appeared to thrive. The hothouse didn't heat the planet evenly. Polar regions warmed enough to melt ice entirely, but equatorial belts bore the brunt of solar radiation. Ocean circulation patterns changed as temperature differences between poles and tropics decreased. This slowed global currents, reducing the mixing that delivered oxygen to deep waters. In the stagnant depths of Panthalassa, life began to suffocate. Hydrogen sulfide-producing bacteria thrived, spreading toxic conditions across the seabed. What began as warming now turned into a cascade of suffocation. As the Permian drew toward its close, volcanic activity intensified dramatically. The greatest eruptions of all would come from Siberia. But even before that, regional outpourings of lava and gas injected pulses of carbon into the sky. Each pulse pushed global temperatures upward, perhaps by several degrees, in geologically short intervals. The climate oscillated violently, brief cool spells followed by scorching rebounds. These fluctuations placed relentless pressure on ecosystems already stretched thin. Getting by in this world meant being able to move quickly and keep going for a long time. The dicynodonts went from continent to continent looking for new plants to eat. Small, warm-blooded early cynodonts sought at night to avoid the heat of the day. So they wouldn't lose as much water, plants developed thicker cuticles. To eat new, hardy plants, insects evolved special mouthparts. The Permian hothouse wasn't just one terrible event, it was a long series of changes that had to be made. Only people who could deal with extremes made it through. Atmospheric shifts. The sky during the Permian was like a science experiment that went wrong in slow motion. At first, the balance between oxygen, carbon dioxide and nitrogen was stable, but over time, things started to go wrong, changing the planet's habitability from top to bottom. While the Carboniferous woods were still lush, the atmosphere started to lose oxygen and gain carbon. This silent change would suffocate the seas, starve fires, and push land life to its limits. During the late Carboniferous, oxygen levels had soared to nearly 35%, far higher than today's 21%. This abundance fueled giant insects, lush swamp forests, and an abundance of life that thrived on quick combustion. But by the early Permian, that oxygen high began to fade. The collapse of coal-forming wetlands and a decline in global photosynthesis meant less oxygen production. At the same time, volcanic outgassing and the oxidation of vast organic deposits drew down what remained. By the late Permian, oxygen may have plunged to as low as 15%, barely enough to sustain large, active animals. For creatures of the time, this thinning air was more than an inconvenience. It altered how they breathed, moved, and even evolved. Amphibians with inefficient lungs struggled. Many vanished from drier regions. In contrast, reptiles and therapsids with more advanced respiratory systems flourished, capable of extracting oxygen from thin air. These physiological advantages became the dividing line between survival and extinction long before the Great Die-Off struck. Meanwhile, carbon dioxide surged. Early volcanic eruptions across Pangea released vast quantities of CO2. But the late Permian saw something unprecedented: the slow ignition of buried carbon stores. As global temperatures rose, permafrost and methane hydrates released additional greenhouse gases. The atmosphere thickened, trapping even more heat in a feedback loop that spiraled upward. Estimates suggest CO2 levels exceeded 2,000 parts per million, roughly 5 times higher than today's average. The result was relentless warming and a planet that could no longer cool itself effectively. Chemical changes in the air also affected the oceans. As carbon dioxide dissolved into seawater, it formed carbonic acid, lowering the pH and making it harder for organisms to build calcium carbonate shells. Corals, sponges, and shelled plankton suffered first. Their decline weakened food webs, cascading upward to fish and larger predators. The sea that had once sparkled with life turned cloudy and hostile, a warning signal recorded in every Permian limestone bed. Dust and ash further polluted the sky. Seasonal fires driven by lightning and drought filled the atmosphere with soot that blocked sunlight for months. When volcanic eruptions followed, sulfur aerosols added their own veil, briefly cooling the surface before more CO2 reheated it. These chaotic swings, short cold snaps followed by surging heat, stressed ecosystems beyond endurance. Plants adapted to one extreme found themselves unprepared for the next. The stability that life depends on was dissolving molecule by molecule. The falling oxygen content even changed how ecosystems burned. Fires that once raged easily in oxygen-rich forests became weaker, allowing more vegetation to accumulate. This increased fuel load then burned explosively when conditions aligned, releasing vast pulses of carbon into the sky. The planet oscillated between suffocation and combustion, a deadly rhythm repeated until balance finally broke. There is proof for these changes in the atmosphere in the form of both geochemical marks and artifacts. Animal dens get shallower, which means that deeper caves didn't have enough air to breathe. Fossil wood has very thin growth rings, which means that the metabolism was slower and the growing seasons were shorter. The number of different kinds of insects also dropped, and the air that used to support giant dragonflies could no longer lift them. Living things were being squished by their own environment. For Earth's climate system, these changes were irreversible on short timescales. With so much carbon in circulation, cooling could only occur if new rock weathering or photosynthesis drew it down. Processes that require millions of years. The Permian sky had effectively locked the planet in a greenhouse. Oceans stagnated, winds slowed, and rainfall patterns fractured. A once dynamic world was slipping into thermal and chemical paralysis. Mountain building continues. The weather above became unstable, and the land below Pangea's shell was also very unstable. The Permian world wasn't just one big, quiet rock. It was made up of mountain chains that formed when rocks crashed into each other and squished together. Every fold in those rocks was made by a fight between countries in the past. Even though the Great Assembly of Pangea was over, its wounds were still fresh. Fault lines shook, rock roots moved, and whole areas shook up because of forces that wouldn't go away. The Northern Hemisphere bore some of the grandest ranges. Along what would one day become Europe and North America, the Variscan Appalachian Belt stretched thousands of kilometers, a serpentine chain built from the collision of Laurisia and Gondwana. Those mountains towered over a landscape already shaped by erosion, their summits shedding sediment into nearby basins. Rivers carried the debris eastward and westward, filling shallow seas with sand and silt. Each layer told a story of grinding rock and restless earth. Farther east, the Ural Mountains emerged where the Siberian Craton rammed into the Kazakh and European plates. The collision locked continents together, but also stitched a visible seam that still divides Europe and Asia today. During the Permian, the Urals were not the modest peaks we know now. They were as high and raw as the modern Himalayas, crowned with glaciers and snowfields even as the global climate warmed. Their shadow created rain barriers that shaped entire ecosystems on either side. To the west, wetter valleys nurtured forests and rivers. To the east, dry basins stretched toward the growing deserts of central Pangea. In the south, the remains of the Gondwanid orogeny formed mountain arcs across what are now South Africa, Antarctica, and Australia. These ranges told of continental compression that rippled outward from Antarctica's still cold heart. Even as ice sheets dwindled, tectonic activity persisted, dragging landmasses northward. The combination of uplift and erosion created a constant flux of sediment. New basins opened while others filled. Life in these shifting landscapes had to keep moving, adapting to rivers that vanished and mountains that rose overnight in geological terms. Volcanism went hand in hand with uplift. Subduction zones along Panthalas's rim released chains of volcanic islands, while continental arcs belched ash and lava across Pangea's margins. These volcanoes did more than shape the land. They fed the atmosphere with gases that tipped the climate further toward chaos. Each eruption pumped carbon dioxide skyward, while sulfur aerosols briefly dimmed sunlight before dissolving into acid rain. The planet's engine, once a source of renewal, had become a steady leak of poison. Yet mountain buildings also carved beauty from destruction. With every uplift came new rivers, new valleys, and new habitats. Erosion from the highlands delivered minerals that enriched distant floodplains, feeding plant life and the animals that grazed upon it. In this way, mountains acted as both destroyers and life-givers, driving cycles of fertility across Pangea. Fossil pollen carried in river sediments shows that vegetation flourished in the lee of mountain ranges, creating isolated ecosystems that evolved unique species. The interplay between mountains and climate was powerful. As ranges grew taller, they disrupted air circulation, redirecting monsoon systems and deepening continental droughts. Some regions that had once received steady rainfall now baked under constant sun because new peaks blocked the moisture-laden winds. Elsewhere, warm, moist air cooled as it rose, condensing into torrents that carved gorges down the slopes. These regional contrasts added another layer of complexity to an already unstable world. Narrow continental shelves. Pangea's tall mountains fed rivers that brought huge amounts of sand and silt into the seas nearby. The Permian world, on the other hand, didn't have much room for the sea to spread out like the broad, shallow coastal edges of earlier times. When all the big land masses came together to form one supercontinent, they squished the seas into deep pools, leaving only thin strips of shallow water along the coasts. These very thin shelves, which are sometimes only a few dozen kilometers wide, became the lifelines of many marine species. They were important for all coral-like sponge, brachiopod, and fish species. To understand why these shelves mattered, it helps to imagine Earth's geography from above. Pangea formed a massive C shape, hugging the inner Paleotethous Sea to the east and facing the immense Panthalassa Ocean to the west. Between land and deep water stretched just a thin strip of sunlight-filled sea, the perfect zone for reefs, carbonate platforms, and sedimentary life. Here, warm temperatures and gentle waves supported thriving ecosystems. Yet, their narrowness made them fragile. When sea levels dropped or local climates changed, entire habitats vanished in a geological blink. The sedimentary layers from these margins reveal constant struggle between land and sea. Coarse river sands alternated with fine marine limestones, marking the back-and-forth rhythm of transgressions and regressions. During wetter monsoon phases, rivers swelled and pushed fresh water far offshore, forming deltas that fed nutrient-rich blooms. During dry phases, sea levels receded, exposing mudflats that baked in the sun. Over time, this cyclical dance built intricate rock records, each layer a heartbeat in the slow pulse of Permian seas. Reefs clung to these margins like lacework on stone. Built by sponges, bryozoans, and algae, they formed massive structures rivaling the coral reefs of today. Each reef was an entire world, outer slopes patrolled by ammonoids and fish, inner lagoons hosting starfish, crinoids, and shell beds. Fossils from regions like the Capitan Reef in Texas and the Ural margin show that these ecosystems were remarkably complex. Some sponges grew into towering domes. Others formed honeycomb textures that anchored sand and shells together. When one generation died, its skeleton became the foundation for the next. Yet narrow shelves meant limited space. Marine species crowded into small geographic ranges, often restricted to particular coastlines or basins. This made them highly vulnerable to local disturbances. A shift in temperature or salinity could wipe out an entire regional ecosystem. When volcanic gases later acidified the oceans and lowered oxygen levels, these confined habitats were among the first to collapse. The very architecture that had made Pangea's coastline stable, steep slopes dropping quickly into deep water, also left little refuge for migrating life. Ocean currents along these shelves were equally extreme. Because Pangea spanned from pole to pole, its coastal circulation linked icy southern waters with equatorial warmth. Upwelling zones along western margins delivered nutrients from the depths, sustaining plankton that fed the food web. But in the restricted seas of the Paleotethys, circulation could stagnate. Without regular renewal, oxygen dropped, and black, organic-rich muds formed on the seafloor, an early warning sign of the mass anoxia that would later engulf the world's oceans. Sedimentologists studying Permian rocks see a pattern of periodic crisis even before the final extinction. Reef gaps, collapsed carbonate platforms, and abrupt faunal turnovers hint at recurring stress events. Sometimes these were driven by rapid sea level changes, other times by regional warming or ash fallout from distant volcanoes. In every case, the narrow shelves acted as amplifiers, translating small environmental shifts into catastrophic biological consequences. Still, these beaches stayed alive for most of the Permian. Hybodont shark schools searched near the edges of the reef, and their shadows moved quickly through the sponges. Nautiloids moved in beautiful spirals, and echinoderms moved with the flow of gentle currents. As the sun moved through the clear, warm water, it lit up the bottom with shimmering patterns of brachiopods and clams. It was a world full of colour, complexity, and quiet work that was about to fall apart, but was doing well for now because of the careful balance it was in. Reef builders of the Permian. The Permian seas were warm and shallow. Below the surface, huge reefs that were alive with colour and movement rose from the water. But these weren't coral islands like we know them. There weren't many real corals yet. Instead, sponges, algae, and a strange mix of bacteria ruled the ocean floor. Their huge mounds went on for kilometres and created complicated habitats where almost every marine species could find food, protection, or a place to lay eggs. During a time when land was dry, the sea made its own stone gardens. Sponge species, especially the very efficient calcareous and glass sponges that produce silica and calcium carbonate into complex structures, built these reefs. Modern reef builders depend on sunshine and plants that live together. But Permian sponges could build in both clear and murky water. They formed dense thickets across continental shelves by growing in different shapes, such as spreading, swollen, and fan-like. Over time, these groups of sponges hardened into walls that were tens of meters high. They built on top of each other until they were like underwater rocks. Algae added color and cohesion to the mix. Red and green calcareous algae wove themselves between the sponge's skeletal lattices, acting like living mortar. Cyanobacteria, the same microbes that once oxygenated Earth's atmosphere, coated surfaces with slimy mats that trapped sediment and strengthened the structure. Together, they created ecosystems that were astonishingly stable for millions of years, resistant to erosion, adaptable to changing currents, and capable of rebuilding quickly after storms. The Capitan Reef, now exposed in the Guadalupe Mountains of Texas, remains one of the best examples. In its prime, it curved along the edge of the Delaware Basin, facing the open Panthalassa Ocean. Life within it thrived in layers. Outer walls of sponges battered by waves, interior lagoons rich with crinoids, brachiopods, and gastropods, and sandy flats where small fish darted between shadows. The entire structure functioned like an organic machine, each organism supporting another, recycling nutrients and maintaining the balance that allowed it to persist for millions of years. Reefs grew differently depending on local conditions. In the Tethys region, modern China and the Middle East, reefs often took on dome shapes or pancake-like platforms floating near the surface. In colder southern waters, smaller patch reefs dotted the coasts of Gondwana, dominated by hardy algae and encrusting organisms rather than towering sponges. No matter the form, all shared one trait: efficiency. In a world with limited shallow seas, they made the most of every available metre of space. The productivity of these reefs supported an entire food web. Ammonoids hunted above them, their shells coiled like ornate fossils waiting to happen. Tiny foraminifera filtered plankton in the sunlit lagoons, while trilobites clung to cracks and crevices, their last evolutionary stronghold. Crinoids waved feathery arms to capture drifting particles, and fish schools flashed like living mirrors between sponges. The diversity was staggering and fragile. Geochemical evidence shows that these reef systems experienced occasional stress long before the final extinction. Shifts in oxygen levels, spikes in temperature, and brief pulses of ocean acidification periodically thinned reef communities. Still, they always rebounded until the end of the Permian. When the Siberian traps erupted and greenhouse gases spiked, the delicate balance broke. Warm, acidic, anoxic waters swept across continental shelves. Sponge frameworks dissolved, algal binders perished, and reefs collapsed en masse. It was the first global reef extinction in Earth's history, wiping out the very foundation of shallow marine life. The reef builders from the Permian show how strong life can be, but sometimes even the greatest systems can fail when things change faster than nature can react. It was the heart of shallow water, the lungs of the ocean floor, and the stage for endless stories of evolution. As soon as they died, there was silence in Panthalassa, marine workhorses. The real workers of the Permian seas were the benthic workers who kept marine life going. They did their work in the shadow of the sponge reefs. In prehistoric times, these weren't the flashy top hunters. Instead, they were the hard-working builders, cleaners and recyclers that kept the seas beat. There were brachiopods, bryozoans, crinoids, ammonoids, and fusulinids living on every inch of the seabed. The living things in the ocean used sunshine and silt to make food, energy, and the balance that kept the ocean alive. Brachiopods were the backbone of this workforce. They looked like clams, but their internal anatomy told a different story. Two shells enclosing a lopophore, a delicate feeding organ that filtered microscopic food from passing water. In the Permian, brachiopods blanketed the seabed in astonishing numbers. Entire limestone layers consist almost entirely of their shells. Some species form dense brachiopod carpets, stretching for kilometers, their valves clacking softly in the current. Though simple, they were masters of efficiency, surviving in waters too cool, shallow, or murky for other animals. Among them lived the bryozoans, colonial creatures that resembled lace or coral. Each colony was made up of hundreds of tiny zooids working together, filtering nutrients and building calcium carbonate skeletons in intricate fan or net shapes. Bryozoans glued themselves to shells, rocks, and even each other, adding another layer of complexity to the seafloor. They provided both food and shelter for small crustaceans, worms, and juvenile fish, a living foundation that multiplied life wherever it grew. Floating just above the seafloor, the crinoids waved like underwater flowers. Related to starfish, these sea lilies anchored themselves with stalks and unfurled feather-like arms to capture drifting particles. Their meadows could be as dense as terrestrial forests, swaying in unison with the currents. Fossil beds from Kansas to the Urals are filled with their segmented stems, each disc once part of a living canopy that filtered the ocean's flow. Crinoids turned the gentle movements of water into a conveyor belt of nutrition, transforming plankton into the energy that powered the rest of the food chain. Higher in the water column, the ammonoids ruled. Coiled like works of art, these cephalopods were the fast movers of the Permian seas. Propelled by jet-like bursts of water, they hunted small fish and crustaceans with quick precision, guided by sharp eyes and clever tentacles. Their shells weren't just beautiful, they were engineering marvels, divided into chambers that allowed buoyancy control. Each new coil recorded a chapter in their life, and their global distribution makes them perfect time markers for modern paleontologists. Alongside them swam the last of the nautiloids, survivors from far earlier oceans, spiraling through the currents like ghosts from the deep past. The fusulinids were one of the smallest but most important groups in this marine machine. Just a bit bigger than a rice grain, these foraminifera had only one cell. They made calcium carbonate shells that looked like tiny footballs. Still, there were so many of them that it was hard to believe. When they died, billions and billions of them sank to the bottom and left behind thick layers of limestone that make up whole mountain ranges today. Each shell is a fossilized miniature of the ocean during the Permian period. It shows how hot, cold, and time-related things were. Even though they were very small, they made continents out of their leftovers. Trilobites, the icons of Paleozoic seas, were fading by this time. Only a few small species lingered in cooler waters, their once diverse lineage now reduced to relics. They shared the seabed with burrowing worms and mollusks, creatures that constantly stirred the sediment, oxygenating it and recycling nutrients. These humble scavengers and filter feeders sustained the delicate balance that allowed predators to thrive above. Without them, the seas would have turned stagnant long before the Great Extinction ever arrived. These sea creatures worked together to make the Permian Ocean a complex web of movement and trade. Each group had a specific job to do. Bryozoans built, crinoids gathered, ammonoids hunted, and fusulinids kept track of things. The way they interacted with each other built the biological framework of the time. These creatures were the first to notice when conditions changed, like when oxygen levels dropped or carbon levels rose. Their fossils are like an early warning system that has been kept in stone. They show exactly when and how the ocean started to weaken. Sharks and bony fishes. If the reefs and benthic workers were the ocean's base, then its masters swam above. They were sleek, restless hunts who filled every current from the lagoon to the abyss. Since the Devonian, sharks and other bony fish had lived through every major change in the environment. By the Permian, they had mastered the seas. While these animals weren't the biggest in the Mesozoic just yet, their shapes and behaviours set the stage for all the bigger animals that came after, like great white sharks, coelacanths, and lungfish today. The most common sharks of the time were the xenocanths, long-bodied predators that dominated freshwater and coastal environments. Picture a shark built like an eel, with a ribbon-like fin running the length of its back and a peculiar spine jutting from its head like a dagger. That spine likely served as defense against larger hunters, or perhaps helped sense electrical fields in murky rivers. Xenocanths were ambush specialists, gliding silently through swamps and deltas before striking at amphibians and smaller fish. Fossilized teeth, narrow, twisted, and sharp, appear across Pangea, a sign of how well these hunters adapted to both tropical rivers and high-latitude lakes. In marine realms, hybodont sharks took the crown. Sleek, fast, and versatile, they were the predecessors of many modern shark families. Their mouths carried two sets of teeth, pointed ones for catching prey and flatter ones for crushing shells. This dual arsenal let them shift diets depending on local abundance, a key advantage in unstable environments. Hybodonts patrolled coral-like reefs and open shelves. Tissue bodies rarely turned into fossils, but the sheer number of teeth they have tells us a lot about them. There may be thousands of teeth in a single bed of limestone. Each tooth is an experiment in form that evolved over time. Alongside them swam the rising stars of the era, the bony fishes, both actinopterygians, ray-finned, and sarcopterygians, lobe-finned. The ray-finned fishes were lean and efficient, with light skeletons and flexible fins supported by thin rays. They maneuvered with delicate precision, flicking through reef crevices and river channels. Early relatives of modern sturgeons, gars and bowfins appeared in this period, proving the adaptability of the design. Their scales, thick and rhomboid, reflected light like metal armour, an evolutionary counter to the sharp teeth of predators. The lobe-finned fishes represented a different legacy. Heavier and more muscular, they bore fins with internal bones and joints, precursors to limbs. Coelacanths and lungfish were the most famous of their kind. Coelacanths patrolled deep reefs and outer shelves using slow, deliberate movements to hover near prey. Their powerful tails allowed sudden bursts of speed, while their paired fins moved in alternating rhythm, almost like walking underwater. Lungfish, on the other hand, became masters of survival. With primitive lungs, they could gulp air during droughts, burrow into mud, and wait out the dry season. In the fluctuating Permian climate, such traits meant the difference between extinction and endurance. Predator-prey dynamics among these groups created constant evolutionary tension. Armoured fishes developed thicker scales, sharks responded with serrated teeth. Some ray-finned species evolved elongated snouts to probe reef crevices. Others flattened their bodies to blend into the sand. Even colour likely played a role, camouflage for ambush, shimmer for confusion. The Permian oceans, though not yet home to dinosaurs or whales, already mirrored the ecological complexity of today's seas. Fossil sites such as the Mecca Quarry in Kansas and the Kupferschiefer of Germany preserve entire aquatic communities, frozen mid-motion. Hybodonts with bellies full of fish, lungfish cocooned in dried mud, and schools of ray-finned species trapped by sudden anoxic events all tell of oceans both bountiful and perilous. Each species honed its advantage, and yet none could outrun the environmental storm building over their world. Flourishing insects. During the Permian, the skies and woods were full of a different kind of energy than the seas, which were full of sharks and old fish. It was the best time for insects, the first real explosion of life in the air. From swamps to deserts, every environment was alive with them. The hum of flight became the background music of the Permian world as wings sparkled in the sun and teeth clicked in the thorns. By now, insects had evolved nearly every modern innovation. They had conquered air, land, and even the margins of fresh water. The Carboniferous giants were gone. Oxygen levels had fallen too low to sustain dragonflies the size of hawks, but diversity had exploded. The Permian's insects weren't the largest, they were the most adaptable. Beetles chewed through wood, cockroaches thrived in every crack, and early relatives of flies and true bugs experimented with mouthparts designed for piercing, sucking, and siphoning. The forests of conifers and seed ferns served as both habitat and pantry. Winged termites and wood-boring beetles decompose fallen trunks, recycling nutrients into the soil. The first herbivorous insects, ancestors of modern leafhoppers and cicadas, pierced plant tissues to drink sap. Their feeding left distinctive scars in fossilized leaves, silent records of the earliest insect-plant warfare. Some insects evolved camouflage so convincing that even their fossilized wings still show outlines of leaf veins that once hid them from predators. In the drier regions of Pangea's interior, insects became masters of endurance. With exoskeletons coated in waxy layers, they retained water under the brutal desert sun. Burrowing beetles and primitive mantises hunted in twilight hours, while locust-like orthopterans, early grasshoppers, formed swarms that could strip entire fern groves. The atmosphere's low oxygen content forced smaller body sizes, but it also encouraged efficiency, rapid life cycles, higher reproductive rates, and specialized diets. Evolution rewarded adaptability over size. Pollination, still in its infancy, was beginning to reshape the landscape. True flowering plants would not appear for another 100 million years, yet Permian insects already practiced the basic art. Gymnosperms like seed ferns and cycads produced pollination droplets, sugary secretions that drew small insects to their cones. Some species of beetles and scorpion flies likely transferred pollen unintentionally as they fed, an early rehearsal for the grand botanical symbiosis that would later dominate Earth's ecosystems. Predation followed the normal rule of evolution. Hunters show up where there is food. Dragonflies were still flying killers, even though they were smaller than their Carboniferous ancestors. Because their legs were spiny and their eyes were big, they could catch their food in the air. Robberfly ancestors watched from the sky, and early mantid cousins hid among the leaves to attack by surprise. Coprolites, which are fossilized droppings, sometimes have pieces of beetle shells in them, showing that even these armored survivors had enemies. In the cooler and wetter southern regions of Gondwana, insect diversity reflected the different vegetation. There, dense forests hosted moisture-loving groups, mayflies, stoneflies, and giant lacewing relatives whose larvae hunted in streams. These insects became vital links between land and water, feeding amphibians and fish alike. Their synchronized emergencies may have been spectacular, blanketing rivers in shimmering wings under the fading Permian sun. The evolution of wings was the ultimate advantage. Insects now used flight not just to escape predators, but to migrate, colonize, and exploit new food sources. Wing folding, an innovation perfected by beetles and cockroaches, allowed better protection and maneuverability. Some species experimented with gliding or hovering, hinting at the future sophistication of flies and bees. The air itself had become a new ecosystem, layered with invisible highways of pollen, prey, and predators. Even their deaths shaped the planet. As insect populations grew, their waste enriched soils, fueling plant growth. Their remains, tiny exoskeletons of chitin, accumulated in sediments, recording climatic changes and atmospheric chemistry. Insects had become both agents and archivists of their age. They connected ecosystems vertically, from canopy to soil, from surface to root. But this golden age had the makings of its own end. For such variety to exist, temperatures had to be stable and air levels had to stay the same. However, these conditions were already breaking down. As late Permian volcanoes erupted more, waves of carbon dioxide and ash messed up ecosystems. A lot of insects went extinct, especially those that lived in damp woods. Fossil records show a big change near the end of the period. This was the first time in Earth's history that the variety of insects around the world dropped dramatically. Seed plant world. The Permian landscape, though battered by droughts and shifting winds, still pulsed with life. From coastlines to high plateaus, the dominant form of vegetation was no longer the swampy ferns of the Carboniferous, but a new, tougher generation of seed-bearing plants. These pioneers, glossopterids, conifers, ginkgophytes, and cycads, reshaped the continents. Their roots stabilized soils, their leaves slowed erosion, and their seeds unlocked survival in a climate where water had become a rare treasure. The key to their success was independence from water for reproduction. Unlike their spore-bearing ancestors, these plants didn't need open pools or constant rain to propagate. Their seeds carried embryos wrapped in protective coats, ready to wait out months or years of dryness before sprouting. It was the single greatest evolutionary leap in the history of plant life, and it allowed forests to conquer the farthest edges of Pangea's deserts. Among the giants of this new flora stood the glossopterids, trees with broad, tongue-shaped leaves that formed dense forests across the southern supercontinent of Gondwana. Their fossils cover what are now India, Australia, South Africa, and Antarctica, uniting those regions under a single paleobotanical signature. Glossopterid leaves littered ancient floodplains, creating thick peat layers that later became coal seams. Each leaf's fine venation hints at adaptation for efficient water transport, a necessity in climates swinging between flood and drought. Their seeds, born on specialized structures, suggest early attempts at directed pollination, possibly aided by insects. Farther north, on drier ground, conifers began their long reign. Early relatives of pines and araucarias spread across uplands, their needle-like leaves minimizing water loss and their tall, tapering trunks rising above most other vegetation. Their cones protected seeds from both fire and drought, while thick bark shielded them from the frequent lightning strikes of Pangea's stormy atmosphere. Some conifers grew in pure stands, creating forests of dark green spires against red desert sands. Others mingled with cycads and ginkgophytes in mixed woodlands, providing shade for smaller shrubs and primitive flowering ancestors. The cycads, Palm-like plants with stout trunks and spiral crowns of stiff leaves added variety to these landscapes. Though often mistaken for palms, they were more ancient, living fossils that still persist today. In the Permian, cycads thrived in semi-arid belts, their tough cuticles and slow metabolism ideal for heat resistance. Fossil cones suggest they reproduced with help from insects, marking another step toward the pollination systems that would dominate future ecosystems. The ginkgophytes, ancestors of the modern ginkgo, formed another distinctive group. With fan-shaped leaves and branching veins, they tolerated both cold and dry conditions, a rare versatility in the Permian world. Their seeds, encased in fleshy coatings, may have been dispersed by reptiles or small synapsids, establishing one of the earliest plant-animal partnerships. Even today, the lone surviving ginkgo species carries echoes of that ancient resilience. These seed plants changed the planet's carbon cycle as a whole. Their deep roots stored carbon dioxide from the air in the soils and rocks, and their wood kept carbon locked away for hundreds of years. At the same time, their power changed how oxygen is made around the world. Once upon a time, large wetlands pumped oxygen into the air. Now, wooded woods and drier areas slow that flow, adding to the slow decline of the atmosphere that was already happening. The plants were perfectly adjusting to their surroundings, but they were also changing them without meaning to. In the highlands near the Ural Mountains and the Karoo Basin, seasonal patterns shaped entire biomes. During wet seasons, rivers flooded valleys and forests flourished. During dry months, leaves fell, soils cracked, and fires swept the landscape. Charcoal layers from this era reveal widespread wildfires, a natural consequence of arid climates and oxygen levels that, though declining, still supported combustion. Afterward, quick-sprouting species reclaimed the ash beds, continuing the endless cycle of death and renewal. Amphibians hold on. Even though snakes and therapsids took over the land, the Permian frogs didn't go away quietly. They lived where water pooled, like in shady deltas, floodplains, and seasonal lakes. They were descended from the great Carboniferous swamp dwellers. Even though the sky was getting hotter and dry, their kingdom was shrinking. To stay alive, they changed in amazing ways. Because they didn't give up, they became living fossils of a world that was dying, creatures stuck between two ages. The giants among them were the temnospondyls, a diverse order ranging from crocodile-sized predators to small frog-like insect hunters. Some species, like Eriops of North America, grew up to 2 meters long, with heavy skulls and sprawling limbs built for ambush. Fossil trackways show them crawling across muddy banks, waiting motionless for prey to stray near the water's edge. When they struck, they did so with sudden ferocity, snapping fish, amphibians, or even small reptiles in their wide, tooth-lined jaws. Their thick skin, more resistant to drying than that of earlier amphibians, allowed them to stray farther from the water during brief forays onto land. In wetter southern regions, particularly in Gondwana, the rhinesuchids and prionosuchids took amphibian design to monstrous extremes. Prionosuchids, known from Brazil, stretched over 6 meters in length, resembling primitive crocodiles with elongated snouts filled with needle-like teeth. They ruled the rivers as apex predators, preying on fish and other amphibians. Their presence shows that even as reptiles diversified, amphibians still dominated certain aquatic niches. But their world was confined. Each drought, each shift in monsoon rhythm tightened the boundaries of their survival. Smaller amphibians thrived in the margins between land and water. The disaurophoids, with lighter bodies and stronger limbs, were early experiments in terrestrial living. Some had protective scales on their bellies to reduce moisture loss. Others evolved burrowing habits to escape the sun. These groups likely gave rise to the ancestors of modern frogs and salamanders, a lineage that would outlast even the Permian apocalypse. Their fossils appear in high numbers near seasonal ponds and floodplain sediments, evidence that they time their life cycles to fleeting rains. It cost a lot to adapt though. The frog kingdom that used to be worldwide had broken up into many smaller empires, each with its own rivers, lakes and oases spread out over hundreds of kilometres of desert. Reproduction stayed connected to water. Eggs dried out when there were no standing ponds. In many places, frogs went extinct and were replaced by snakes whose amniotic eggs made them not need water to survive. Being able to live without going back to the water was the clear line between power and decline. Some species may have evolved skin capable of partial gas exchange even in dry air. Others, like certain temnospondyls, developed broad, flat skulls that acted like natural radiators, dispersing heat through surface blood vessels. A few became fully aquatic, retreating to deep lakes that stayed cool year-round. The fossil record suggests they used estivation, burying themselves in mud during droughts to endure harsh seasons. When the rains returned, so did their croaks, echoing across floodplains as the ancient rhythm of amphibian life resumed. Amphibians also played a crucial ecological role. They linked aquatic and terrestrial food webs, feeding on insects and serving as prey for reptiles, therapsids, and fish. Their eggs and larvae nourish countless scavengers, while their decomposing bodies enrich sediments. Even as their numbers declined, they remained an essential thread in the fabric of Permian ecosystems, a bridge between waters past and land's future. But things were changing too quickly in the world around them. As volcanic gases made rain more acidic, deserts grew, lakes dried up, and the chemistry of the water changed. Fossil frog diversity rose in the middle Permian and then dropped sharply after that. In the Karoo and the Russian platform, areas that used to be very green, only a few hardy genera made it through to the late Permian. They hid in remote areas where rainwater or springs with shade still existed. Synapsid takeover in early Permian. Long before dinosaurs or mammals, the land was ruled by a strange family of animals that were neither reptiles nor mammals, but something in between. They were called synapsids, and in the early Permian, they ruled all of Earth's regions without a doubt. Their heads had a single temporal opening behind each eye. This was a feature that evolved over time to make their jaw muscles stronger, which led to smarter and faster hunts. This group of early synapsids ruled every area, from the swamps of North America to the floodplains of Russia. The earliest of their kind were the pelycosaurs, a diverse group that looked like a cross between a reptile and a dragon. The most famous, Dimetrodon, stretched up to 3 meters long and carried an enormous sail along its back, an array of elongated vertebral spines connected by skin. This sail may have helped regulate body temperature, absorbing the morning sun and radiating heat at dusk. Others suggest it served as a display for mating or intimidation. Whatever its purpose, it made Dimetrodon one of the most recognizable predators of the Paleozoic. With serrated teeth, powerful limbs, and a crocodilian gait, it ruled the riversides as the apex hunter of its age, but not all pelycosaurs were carnivores. The Adaphosaurs, close relatives of Dimetrodon, were among the earliest large herbivores on land. They too bore sails, though their teeth were blunt and peg-shaped, ideal for grinding tough vegetation. Fossils show deep barrel-like rib cages, evidence of large digestive systems for processing fibrous plant matter. Adaphosaurs grazed in herds across lowland plains, browsing on ferns and seed plants. For the first time in Earth's history, land ecosystems supported both giant herbivores and giant predators, linked in a complex web that resembled the modern savanna. Other pelycosaurs filled every gap in between: insectivores, scavengers, and opportunists. Their evolutionary flexibility came from that single skull opening, an innovation that allowed stronger, more complex jaw muscles, enabling more powerful bites and varied diets. This subtle anatomical change would eventually give rise to the chewing precision of mammals. The groundwork for warm-blooded life was being laid, one bone at a time. The fossil record from early Permian sites, like Texas's Red Beds, tells a vivid story. Skeletons of Dimetrodon lie scattered near the remains of Edaphosaurus, as if frozen mid-chase. Freshwater fish, amphibians and small reptiles fill the same strata, showing a balanced, thriving ecosystem. It was a time when synapsids reached their first golden age, fast, adaptive and ecologically dominant, but the environment was already testing them. Temperatures fluctuated sharply, droughts shortened the wet seasons. The sprawling pelycosaurs, with their large bodies and limited water retention, were tied to rivers and deltas. When climates turned more arid, survival demanded change. Natural selection favoured synapsids that could regulate body temperature better, conserve moisture, and move efficiently across dry terrain. The next evolutionary chapter, the therapsids, would emerge from this crucible. Some transitional forms already hinted at what was to come. Smaller, more agile species showed upright limb postures and differentiated teeth, incisors, canines and molars, that allowed finer control over food. Bone histology reveals higher metabolic rates than in reptiles, suggesting early experiments in warm-bloodedness. They no longer basked for heat, they produced it. Evolution was shifting gears. By the end of the early Permian, pelycosaurs began to wane. Many fell victim to ecological turnover as new competitors, advanced synapsids, adapted to drier climates, took over. But their legacy endured in every jaw muscle and tooth cusp of their descendants. The Permian world had entered an age of innovation, where survival depended not on armour or size, but on physiology and adaptability. Therapsid rule in late Permian. By the middle to late Permian, evolution had crowned a new order of rulers. The pelycosaurs had faded, their sails and slow gaits relics of an earlier world. In their place rose the therapsids, a dynamic, diverse lineage that blurred the line between reptile and mammal. They breathed deeper, moved faster, and thought sharper than any of their predecessors. Their bones tell a story of rising intelligence, warm blood, and complex social behaviours that foreshadowed the mammals yet to come. Therapsids divided into multiple clans, each carving out a different niche across Pangea's shifting continents. Among the most successful were the dicynodonts, the great herbivores of their time. Stocky and muscular, they bore turtle-like beaks for cropping vegetation and a pair of protruding tusks used for defence or digging up roots. Some, like Lystrosaurus, could reach the size of a large pig. Others formed herds that roamed the floodplains of Gondwana. Their bones show evidence of growth rings, proof that they endured seasonal hardship, perhaps burrowing or migrating when drought came. With short, sturdy legs and partially upright postures, they were remarkably efficient walkers, perfectly adapted to life in a world swinging between flood and famine. They were up against the finest hunters of the Permian, the gorgonopsians. These hunters, with saber-toothed cats, were sleek, quick and very good at what they did. They had long canine fangs and flexible arms that were held more vertically under their bodies than any other lizard. This made them fast and accurate. The biggest species, like the Russian Inostrancevia, was over 4 meters long and could kill food as big as a dicynodont with a single, crushing bite. Their heads were very specialized. They were light but strong, and their teeth had serrations on them to cut through skin. In a world full of slow snakes and wide-ranging amphibians, the gorgonopsians were the first hunters that really looked like mammals. They had long-lasting strength, good eyesight, and a smart mind. Sharing their ecosystems were the therocephalians, smaller and more adaptable carnivores with short snouts and teeth suited for both meat and insects. Some may have been nocturnal, a hint of warm-blooded metabolism that allowed activity in cooler hours. Fossil evidence suggests that certain species developed whisker pits and glands, early experiments in sensory fur and thermoregulation. The lines between cold-blooded reptile and warm-blooded mammal were blurring fast. Another branch, the dicynodonts, carried the mammalian blueprint even further. They possessed differentiated teeth, incisors, canines, molars, and a secondary palate that allowed them to breathe while chewing, a hallmark of efficient metabolism. Their rib cages and limb bones indicate powerful respiratory muscles and sustained activity levels. Some fossils even suggest parental care. Juveniles found in burrows with adults, implying protection and possibly feeding behaviour. These small, quick creatures could regulate their body heat, maintain higher energy, and think faster than anything before them. They were, in essence, mammals in everything but name. Therapsids didn't just dominate biologically, they reshaped entire ecosystems. The dicynodonts' grazing habits influence plant communities, spreading seeds and maintaining open plains. Predator-prey arms races spurred constant innovation. Thicker hides, faster reflexes, sharper senses. Fossil trackways show complex behaviours: herding, territorial defence, even pursuit hunting. For the first time, land animals were beginning to behave like modern vertebrates, with intricate interactions that went beyond simple survival. In the Karoo Basin of South Africa, one of the richest Permian fossil sites on Earth, thousands of skeletons preserve this thriving biosphere. Dicynodont herds lie fossilised alongside the bones of gorgonopsians, their predator-prey relationship frozen in time. These plains once echoed with life, thundering footsteps, snapping jaws, and the rustle of seed ferns in the hot wind. For millions of years, this was a balanced, functioning world, a glimpse of Earth's future evolution. But that balance wasn't strong. As the amount of carbon in the air rose and oxygen decreased, the late Permian environment started to change again. The dry spells got longer, the rivers dried up, and the lush areas that fed dicynodont flocks died out. A lot of gorgonopsians died when their food disappeared, and others died of heat stress and not getting enough air. By the last few million years of the Permian, the variety of therapsids had started to go down. Their rule was being hampered by the slow approach of disaster, hydrology and soils. The dirt beneath the therapsids' feet told a story of change. During the Permian, the rivers, lakes and floodplains were not fixed landscapes. Instead, they were living systems that changed with the seasons and the weather. Life on Pangea changed the way water moved, and life changed the way water moved. The Earth's drainage and soils changed into a mix of extremes as the climate went from monsoon floods to scorching droughts. There are now braided rivers, salt-crusted lakes, and red, oxidized earth that still colors Permian rocks today. Rivers in this era were wide, shallow, and restless. Instead of single deep channels, they often split into braided networks that wandered across floodplains, carrying massive loads of sand and silt eroded from the rising mountain chains. When the monsoon rains came, these rivers swelled with violent floods, surging across the land in sheets that stripped vegetation and carved new channels. During the dry season, the same rivers shrank to trickles or vanished completely, leaving behind fields of cracked mud and stranded fish. Fossilized ripple marks, raindrop impressions, and desiccation cracks preserved in sandstone are vivid reminders of this alternating rhythm. Floodplains served as nurseries for life. Seasonal pools, called ephemeral lakes, appeared after rains and disappeared within weeks. Amphibians and small reptiles bred in these short-lived waters, and aquatic plants burst into bloom, feeding insects and early crustaceans. When the heat returned, the water evaporated, leaving thin, white crusts of salt and gypsum, minerals that would one day help geologists recognize ancient droughts. In regions like the Karoo Basin, and the southwestern United States, these cycles left entire sequences of alternating sandstone, mudstone, and evaporite, a geological heartbeat of wet and dry. The soils themselves told the same story. Permian soils, known to geologists as paleosols, were among the first to show clear evidence of deep rooting and complex structure. Early forests of conifers and seed ferns stabilized the land, while microbes and fungi broke down organic matter into primitive humus. Yet arid conditions and fluctuating groundwater created unique features. Hard calcareous layers called calcretes formed when calcium-rich water evaporated, binding the soil into stone. In wetter regions, iron oxide stained the ground deep red, a colour that became the signature of Permian landscapes across the globe. Where moisture persisted, soil life flourished. Burrows, root casts, and even tiny fossilised animal tunnels crisscross ancient mudstones, recording a thriving community of decomposers. Millipedes, beetles, and small therapsides all left traces of activity, evidence that the ground itself was alive. These interactions between soil, water, and living organisms help stabilise ecosystems during brief periods of climatic balance. Plants returned quickly after floods, roots penetrated deeper, and rivers became corridors of renewal in an otherwise harsh environment. But the same processes that nourished life also set the stage for disaster. As global temperatures rose and rainfall patterns became erratic, river systems destabilized. In some basins, reduced vegetation allowed massive erosion, washing topsoil into the sea and burying coastal ecosystems under layers of sediment. In others, evaporation outpaced inflow, creating vast salt flats that reflected sunlight and intensified regional heat. Each shift in hydrology disrupted the delicate balance that kept the biosphere functioning. The geochemical record confirms that oxygen levels in groundwater declined toward the end of the Permian, leading to localized anoxia even on land. In these stagnant soils, microbes release methane and hydrogen sulfide, adding more greenhouse gases to the atmosphere. Swamps that once filtered carbon became sources of it, feeding the cycle of warming. It was a subtle but deadly chain reaction, one that turned rivers from life-givers into silent conveyors of decay. Even though there was chaos, the Permian's hydrological network was still what held habitats together. Mountains were connected to seas, and deserts were connected to woods by rivers. Rivers also carried minerals and kept migrant routes open. Fossilized river deltas from this time show signs of both water and land animals living together. For example, lungfish caves can be found next to therapsid footprints, and frog tracks can be found crossing over reptile trails. These points of contact show that water kept the environment together, even though the weather was bad. A normal Permian area had a lot of different types of rocks and soil, a wide, winding river that shines red in the sun. Low conifers line the banks, and their roots dig into the iron-red earth. Dicynodonts walking in groups along dry pathways, leaving marks that would stone up over time. There was a shimmer of heat in the air above, and white salt flats stretched out to the horizon. It was a world that was stuck between water and fire, half alive and half dry. Pre-extinction stress signals. The Earth started to shake in small ways a long time before the big event that ended the Permian. The end of life didn't happen all at once. It weakened, gasped, and stumbled over a long period of time, leaving signs in stone. From the ocean bottom to the tops of the mountains, the Earth was sending out warning signs. Spikes in temperature, air loss, habitat loss, and chemical changes that were bad for almost all living things. Before the fall, these were the shocks that set off the biggest mass destruction in Earth's history. The first of these stress signals appeared in the oceans. Fossilized shells record abrupt changes in oxygen isotopes, evidence of repeated warming events that disrupted circulation. Each pulse raised global temperatures and slowed ocean mixing, suffocating deep-sea ecosystems. layers of dark, organic-rich shale, black, sulphurous and nearly devoid of fossils, mark intervals when entire regions of the seafloor turned anoxic. Bacteria that thrived without oxygen took over, producing hydrogen sulfide gas that poisoned marine life and may have even leaked into the atmosphere. These kill layers stretch across multiple continents, confirming that the crisis was global long before the final extinction peak. Reefs were among the first to crumble. Sponge frameworks that had stood for millions of years began collapsing around 260 million years ago. Species diversity plummeted. Coral-like organisms disappeared entirely. The carbonate platforms that once ringed Pangea's coasts became barren plains of sediment, signalling the breakdown of marine food webs. At the same time, plankton populations fluctuated wildly, reflecting instability in nutrient cycles. When the base of the food chain wavered, everything above it began to unravel. On land, the story was just as dire. Sedimentary layers show increasing signs of drought, thicker calcrete deposits, wider mud cracks, and wind-blown dust preserved between river sediments. Forests retreated, replaced by scrub and open plains. Glossopterid trees that once blanketed Gondwana vanished from the fossil record almost simultaneously. A botanical extinction so sudden that paleobotanists still debate its trigger. With vegetation gone, erosion intensified. Floods scoured valleys bare, sending massive loads of silt into coastal seas. The air itself grew hostile. Volcanic activity intensified across multiple regions, pumping carbon dioxide, methane, and sulfur into the sky. The most destructive eruptions would come from the Siberian traps slightly later, but smaller pulses already destabilized the atmosphere. The result was a greenhouse world laced with acid rain. Chemical weathering increased, washing toxic metals into rivers and contaminating freshwater systems. Fossil soils from this time show elevated levels of mercury, a fingerprint of escalating volcanism. Animal fossils also began to tell a story of attrition. In terrestrial faunas, predator-prey ratios shifted sharply. The great gorgonopsians dwindled, their bones replaced by smaller, more adaptable scavengers. Dicynodont herds shrank in size and diversity. Even insects, Earth's most resilient survivors, experienced their first known mass extinction, losing entire orders of beetles and dragonflies. The pattern was unmistakable. Ecosystems were fragmenting faster than they could rebuild. Paleontologists have found evidence that these environmental pressures occurred in distinct waves. The first, around 260 million years ago, corresponded with the Capetanian crisis, a prelude to the main event that wiped out half of all marine species. It was followed by a brief recovery, then a second, more devastating pulse near 252 million years ago that obliterated 90% of all life. The earlier wave weakened ecosystems, reduced genetic diversity, and stripped the planet of its resilience, ensuring that the final blow would be absolute. Geochemical markers in rocks from this interval show a rise in carbon-12 relative to carbon-13, indicating massive releases of carbon into the atmosphere, likely from volcanic gases and collapsing methane hydrates. The spike in carbon dioxide drove runaway warming. Global temperatures may have risen by 8 to 10 degrees Celsius within less than a million years. The tropics became nearly uninhabitable, the poles ice-free. Even hardy desert-adapted species began to vanish, their tolerance pushed beyond its limits. As the crisis deepened, strange phenomena emerged. Fossilized soils display bleaching bands that suggest acid rainfall. Sediments rich in sulfur compounds point to widespread atmospheric poisoning. Ocean models indicate that hydrogen sulfide may have periodically bubbled to the surface, killing marine organisms and spreading the stench of decay across coastlines. The Earth itself had turned toxic, a system overloaded with its own waste. The Permian world had everything from supercontinents and sponge reefs to saber-toothed cats and dying woods. It was both a masterpiece of evolution and a lesson about how fragile balance can be. It finished in silence, the biggest extinction event the Earth has ever seen. But from that silence, life started again, changing the story of the planet. If you found this trip through deep time as scary and interesting as we did, please like, subscribe, and watch the next part, which is now playing on your screen. Paleontologists have found evidence that these environmental pressures occurred in distinct waves. The first, around 260 million years ago, corresponded with the Capetanian crisis, a prelude to the main event that wiped out half of all marine species. It was followed by a brief recovery, then a second, more devastating pulse near 252 million years ago that obliterated 90% of all life. The earlier wave weakened ecosystems, reduced genetic diversity, and stripped the planet of its resilience, ensuring that the final blow would be absolute. Geochemical markers in rocks from this interval show a rise in carbon-12 relative to carbon-13, indicating massive releases of carbon into the atmosphere, likely from volcanic gases and collapsing methane hydrates. The spike in carbon dioxide drove runaway warming. Global temperatures may have risen by 8 to 10 degrees Celsius within less than a million years. The tropics became nearly uninhabitable, the poles ice-free. Even hardy desert-adapted species began to vanish, their tolerance pushed beyond its limits. As the crisis deepened, strange phenomena emerged. Fossilized soils display bleaching bands that suggest acid rainfall. Sediments rich in sulfur compounds point to widespread atmospheric poisoning. Ocean models indicate that hydrogen sulfide may have periodically bubbled to the surface, killing marine organisms and spreading the stench of decay across coastlines. The Earth itself had turned toxic, a system overloaded with its own waste. The Permian world had everything from supercontinents and sponge reefs to saber-toothed cats and dying woods. It was both a masterpiece of evolution and a lesson about how fragile balance can be. It finished in silence, the biggest extinction event the Earth has ever seen. But from that silence, life started again, changing the story of the planet. If you found this trip through deep time as scary and interesting as we did, please like, subscribe, and watch the next part, which is now playing on your screen.